In this video, we are going to solve a sample problem regarding radiation heat transfer with a simplified approach to view factors and the overall interchange factor. Here's the problem. A circular heater measuring 20 centimeters in diameter has its surface temperature maintained at 1000 degrees Celsius. The bottom of a tank, having the same diameter, is oriented parallel to the heater with a separation distance of 10 centimeters. The heater surface is gray with an emissivity of 0.6, as well as the tank surface with an emissivity of 0.7 with a steady state temperature of 150 degrees Celsius. Determine the radiant energy exchange between the heater and the bottom of the tank if, first case, letter A, the surroundings are black at 27 degrees Celsius. And for letter B, we're going to examine what if the space between the two cylindrical surfaces is enclosed by an adiabatic surface. So let's focus on letter A first. We are going to assume that the surroundings is black, or it's a black body at 27 degrees Celsius. That means that your surroundings will be totally absorbing of any incoming radiation. Now, I have here drawn a simple representation of the problem. The disk at the bottom is our cylindrical heater. And of course, its upper surface is the one that is heating, right? And it's the one that is maintained at 1000 degrees Celsius. For our nomenclature, I'm going to name this surface as surface 1, with T1 being 1000 degrees Celsius. You can imagine that the main application of this system would be for direct radiative heating. Say, for example, if you have a stove top and then you place a pot on top of that, and so this represents your pot and this is your stove, right? So the bottom of the pot, this one, I'm going to call it surface number 2, is the one that is in direct radiative heat transfer with surface number 1. The bottom of your pot is a circle. So I'm going to say that this is maintained at T2 150 degrees Celsius. Essentially, what we have here are two parallel disks that are separated by a finite distance. That distance was also mentioned in the problem, being 10 centimeters. And we do have a simplified approach to determine the view factor using this system right here. Now, view factors can sometimes get complicated, especially if there are multiple bodies that are present in a system. But a very easy way on approaching this would be to just take a look at who are the possible receivers of the radiant energy that is being emitted by surface 1, right? Because surface 1 is the hottest out of all of our surfaces here. So I forgot. Let me also include the surroundings. I'm going to label the surroundings as number 3, or body number 3, with temperature 27 degrees Celsius as mentioned. So if you think of the radiant heat energy that is being emitted by a given surface, you can think of it as any straight line that comes from the surface that emits the energy, right? So if you can draw a straight line coming from surface number 1, you have two possible options. Either the line will go from surface 1 straight to surface 2. That's possible, right? But another possibility is that from surface 1, it would go straight to the surroundings without ever hitting surface 2. That's a very important distinction to make, because that is what we're going to use to understand what view factors are, or how do we make use of the values of view factor, or how do we interpret view factors in general. So since a portion of the energy coming from surface 1 will hit surface 2, and a portion of that will also hit surface 3, then we can say that all of the energy coming from surface 1, I will call that Q1, is simply a sum. Let's call that Q1 net, or the rate of radiant heat transfer coming from surface 1 is simply a sum of the energy leaving surface 1 and hitting surface 2 plus the energy leaving surface 1 and hitting the surroundings. That's Q13. So in my nomenclature here, the first subscript is the source of the radiant energy, and the second subscript is the receiver of the radiant energy. And this also goes the same with view factors. So the total view factor coming from surface 1 is 1, but then this is equal to F12 plus F13. F12 is the view factor from surface 1 to surface 2, and then F13 is the view factor from surface 1 to surface 3. It should make sense that when you add these two view factors together, you get 1 because all of the energy leaving surface 1 can only either go to surface 2 and surface 3, right? There is no possible way of energy to leave surface 1 and also return back to surface 1 within one straight line, right? So that means that there are only two contributors to your view factors. Now, coming from this equation, what we can solve directly is F12, right? Because again, we can assume that our system here are two parallel disks separated by a finite distance, and we do have a simplified figure for that. So I'm referring to the figure in Perry's Chemical Engineer's Handbook. So let me show you my copy of that. This is the 8th edition of the handbook, and this is figure 5-13. In here, we can estimate the view factor using different curves. So we have curves 1, 2, 3, and 4, which represents direct radiation between the two planes. This is our case for letter A. While curves 5, 6, 7, 8 represents planes connected by non-conducting but re-radiating walls. That is our case for letter B later. So let's reserve that for later. We have disks, right? Because the surface of the heater and the bottom surface of the tank are both disks. So that is either curve 1 or curve 5. Curve 1 represents direct radiation between the disks. And curve 1 is the bottommost curve right here in the graph. So all we need to do now is to determine this ratio. The ratio is defined as the smaller side or diameter. We're going to use diameter in this case, divided by the distance between the planes. So let's go back. And let's solve for the ratio. The diameter, since those are two equal planes, right? The diameter is 20 centimeters. And the distance between the two planes is 10 centimeters. We have a ratio of 2. Now let's go to that table. And this is your ratio of 2. You simply take a look at where the x value of 2 will intersect with curve number 1, and then you can read that on the left side for your view factor. So the view factor here, this is 0.2, 0.3, 0.35. This is around 0.38 or around 0.375 because it's directly in the middle of this box right here. Let's just use 0.38 as an estimation of our view factor. So I'm going to say that from that figure, F12 is 0.38. Since we have already established the view factor algebra earlier here, then we can also now solve for F13, which is the view factor from plate number 1 to the surroundings, which is simply 1 minus 0.38 or 0.62. And that is all we need right now in order to quantify the rate of heat transfer from plate 1 to plate 2. Now, we do have to take note that the problem is not asking us for the net amount of energy, right? We are being asked for the radiant energy exchange between the heater and the bottom of the tank, and that is only Q12. So when we write the formula for Q12 or the rate of heat transfer from surface 1 to surface 2, we can write it this way. We need the area of surface 1 and then the view factor from surface 1 to surface 2 times the emissivity of surface 1 times the Stefan-Boltzmann constant times the difference in temperature to the fourth between surface 1 and surface 2. However, this equation right here is only applicable if the receiver of the radiation is a black body. Notice that in this equation, we are only considering the emissivity of the emitting surface, but we are not considering the emissivity of the receiving surface. But in reality, we should consider that as well. So if you take a look at my taped note right here, we call this the overall interchange factor. And according to the formula of the overall interchange factor, we are considering the emissivity of both the emitter, that's emissivity 1, and the receiver, that's emissivity 2. So we are able to convert the simple view factor into an overall interchange factor. And when we factor that into our equation right here, this will now change such that what we are using is the area of the emitting surface times the overall interchange factor, F12, and we no longer have to include emissivity here in the equation for heat transfer because the emissivity is already included in the overall interchange factor. We multiply this by the Stefan-Boltzmann constant times the temperature to the fourth difference. This is T1 to the fourth minus T2 to the fourth. Okay, we don't have to solve for Q13. We're only going to solve for this if we are looking for the net rate of heat transfer coming from surface 1 to both surface 2 and the surroundings. So this is the equation that we will use. Now let's solve for the overall interchange factor because we already do have the normal view factor. So just keep in mind that this normal view factors, the F12 and F13, these are to be used if the receiving body is a black body. Because if it's a black body, then we don't have to worry about the emissivity 2, right? Because it's just equal to 1. That's the emissivity of a black body. So let me copy the formula here for the overall interchange factor. This is 1 over the view factor F12, that's 0.38, plus emissivity of surface 1 was already given, that is 0.6, that's for the heater surface. And then notice that in the formula there is A1 over A2, that is the surface area for this first disk divided by the surface area of the second disk. We are assuming that they are equal disks, so A1 over A2 would just cancel out. And we can proceed with 1 over emissivity 2, which is 0.7 minus 1. Let's calculate this value. That is 1 over 0.38 plus 1 over 0.6 minus 1 plus 1 over 0.7 minus 1. This is our overall interchange factor. It's 0.268. Now, the overall interchange factor is lower in value compared to the normal view factor because the normal view factor assumes that your exchanging surfaces are both black, right? That means that all of the energy being emitted will be absorbed by another surface. But since they are gray bodies, then we do expect a lowering of the overall interchange factor. Excuse me. Now, going back to this rate of heat transfer equation, we can now characterize the area of the emitting surface. Since it's just a circle, I can write this as pi over 4d squared, wherein d is the diameter, that's 20 centimeters, and then the overall view factor, Stefan-Boltzmann constant, and then the temperatures. Now, word of caution for the temperatures here, you have to make sure that your temperatures are in Kelvin and not in degrees Celsius. Or if you're using English units, make sure that they are in Rankine and not in degrees Fahrenheit. Because when you raise the temperature to any power, it has to be an absolute temperature and not a relative temperature measure. Okay? So the resulting value here for the rate of heat transfer will have a unit of watts, because remember that the unit of the Stefan-Boltzmann constant is watts per square meter per Kelvin to the fourth. Kelvin to the fourth will get cancelled out by the temperature here, and the square meter will be cancelled out by the area that we multiplied. And the overall interchange factor has no dimensions or has no units. So we will be left with a unit of watts. Let's calculate. That will be pi over 4 times, I'm going to use my other keyboard here, d squared. My diameter is 20 centimeters. Converting to meters, that is 0.2 squared times the view factor, the overall interchange factor, times the Stefan-Boltzmann constant, which is 5.67 times 10 to the minus 8. This is watts per square meter per Kelvin to the fourth. There is an equivalent of this in the English system, so you might want to use that if you're handling English units. Now, for the temperatures, again, T1 is 1000 degrees Celsius. Do not forget to convert that to Kelvin before raising that to the fourth power. Minus the temperature of the bottom of the pan is 150 degrees Celsius. Do not forget to convert that to Kelvin. This is our answer. It's 1,239 watts. This is only the portion of energy that leaves plate 1 and is intercepted by plate 2. Or we can also characterize this as the rate of radiant heat transfer between surfaces 1 and 2. It's not the total rate of heat transfer, right? Because there's still heat being lost to the environment. If you want to calculate that, you may do so as well. Just keep in mind that the emissivity of the third body of the surroundings is 1. It's a black body. Okay? Now, you might want to take note that the view factor from plate 1 to the third body is larger compared to the view factor from plate 1 to plate 2, right? Because we can imagine that since there is a considerable gap between plate 1 and plate 2, a lot of energy gets lost to the surroundings. So do not be surprised if the value of Q13 is larger than that of Q12. Okay? But that's how we answer letter A. Now for letter B, it's still the same system, but now the space between the two cylindrical surfaces is enclosed by an adiabatic surface. So what do we mean by this? When we say that it's enclosed by an adiabatic surface, we just mean that we are including a material that is non-conducting but is re-radiating. So imagine, I'm going to shift right here. Imagine our system and you place a shield on the side, something like this, in order to prevent excess radiant heat from being emitted to the surroundings. So in the first case, we just let some of the excess radiant energy to be transmitted to the surroundings. But now you placed a material surrounding your two cylinders such that any stray radiation will get re-radiated back into the inside gap between those two plates. Now, not all of the energy that is being emitted by surface 1 will still reach surface 2 because we still have to imagine that some of the energy will be lost in the shielding material, right? But of course, we expect that there will still be some changes in the rate of radiant heat transfer between surface 1 and surface 2. So let me label again our system. This is surface 1. This is surface 2. Still the same temperatures, still the same emissivities. We're still going to use... Excuse me. Sorry for that. It's allergy season for me. So as I was saying, now that we have placed a shielding material, an adiabatic material, to enclose the space between those two surfaces, we don't expect radiation to be emitted to the surroundings anymore. It's just radiation between surface 1 and surface 2, but the view factor will change. So if you go back to our previous solution, we are solving for Q12, right? And earlier, our view factor is 0.38, but take note that this is for direct radiation between the two planes. Now let's reevaluate that view factor from the same figure that we used earlier for radiation with a non-conducting but re-radiating wall. Let me write it here. The re-radiating part is very important here. If you go back to the figure that we used earlier, remember how I mentioned that there are two curves for disks, that's curve 1 and curve 5. Curve 1 is for the direct radiation. Curve 5 is for planes connected by a non-conducting but re-radiating wall. And take a look at the position of curve number 5. Curve number 5 is higher compared to curve number 1, so we can expect a larger view factor for the one with a re-radiating wall. Because come to think of it, for the first case, we just let radiation escape into the surrounding space, right? But now that you place a shielding material, some of that radiation that should have been lost will simply bounce back into the space right here. So it's still the same ratio. The ratio of diameter over the gap is still 2. And if you take a look at the figure, for a ratio of 2, and for curve number 5, this is 1, 2, 3, 4, 5. Curve number 5, this is, you can read the view factor. It's somewhere right here. This is 0.6, 0.7. It can be taken as 0.66. It's not quite equal to 0.65. So let's use 0.66. The new view factor, F12, is 0.66. Now, you don't have to worry about F13 or the view factor to the surroundings because we are not doing that anymore. Now, we just have to take care of the overall interchange factor because your surfaces are still gray bodies. So we still have to account for that. Let's resolve for the new overall interchange factor. Take a look at the formula here. This now becomes 1 over 0.66 plus 1 over 0.6. This is the emissivity of the emitting surface. And then the emissivity of the receiving surface, minus 1. Let's calculate this value. So that is 1 over 0.66. There is a considerable increase in the view factor. So we should also expect that there will be an increase in the overall interchange factor. I'm getting 0.383. If you compare that with the previous value of the overall interchange factor, we definitely have a larger value now. So we can expect a larger value for the rate of heat transfer between plates 1 and 2. We're going to use the same equation. So the radiant heat transfer between plates 1 and 2 is approximated by still the area, pi over 4d squared, times the new overall interchange factor, times the Stefan-Boltzmann constant, times temperature to the fourth, minus temperature 2 to the fourth. Let's substitute all those values in our calculator. That is, we use this, pi over 4 times diameter is 0.2 meters squared times the new view factor, overall interchange factor, times the Stefan-Boltzmann constant, times temperature 1 is 1000 degrees Celsius, convert that to Kelvin, to the fourth, minus the temperature of the receiving surface is 150 degrees Celsius, converting that to Kelvin, and then raised to the fourth power. The answer is 1,771 watts. As we predicted, since we are now placing a non-conducting but re-radiating walls to mitigate some of the lost radiant energy escaping the system, then we are able to increase the rate of heat transfer or the rate of radiative heat exchange between surfaces 1 and 2. As a comparison, for the one without walls, with the energy being lost to the surroundings, or some portion of the energy being lost to the surroundings, this is the amount or the rate of heat transfer between the two plates, and we are able to increase that to 1,771 watts by placing that non-conducting but re-radiating wall. Okay, so this is a very simplified approach to dealing with radiation. So we used a ready-made graph or figure to estimate the view factors, and we made some simplifying assumptions as well when we are using the overall interchange factor to account for non-black surfaces. In reality, problems like this would require an analysis of resistances in series and parallel. So there is also an analog or an equivalent resistance diagram associated with radiation. But this would suffice for very simple calculation and for comparison between rates of heat transfer for different types of system. That is it for this problem. Thank you for listening. I'll see you on the next one.